Thank you very much for this invitation to talk, and I appreciate getting to go after Oscar because he defined a lot of what's happening across Europe and in these programs, and then I get to come in and add a little bit deeper layer with an example from the Leibniz Supercomputing Center. So first and foremost, bonjour from my team. This is our Q crew at LRZ. We're around 30 or so strong. We definitely have more spots open, so if you like what you're going to be hearing soon, come talk to me afterwards because we're always looking for smart people who like big challenges. Also, I'd like to say hello from Munich to Paris. I represent the Munich Quantum Valley. So this is an initiative in the state of Bavaria in Germany. And this is really quite an ambitious effort at the regional level. Effectively, we are pulling together the Fraunhofer organization. We are pulling together Max Planck, Technical University of Munich, LMU. These are two centers of excellence in Germany. Let's see what else. German NASA, DLR, Bavarian Academy, that LRZ falls under. And basically they have pooled the rich history of physics development, research, and capability to develop 3 separate modalities of quantum systems within the same ecosystem. We all work very tightly together, so that's superconducting, ion, and neutral atoms. We have Fraunhofer that's providing a lot of the use cases. We have algorithm developers within our consortia here. And then where I come in from LRZ, we are responsible with TUM, with the Technical University, to build a unifying software stack. And so I'll get to that in just a few moments. But kind of playing on what Oscar has already mentioned, why are we thinking about integrating quantum into HPC? So I can blow over this a bit since Oscar already kind of covered it. Really short, the too long didn't read version is that it's good for quantum computers and it's good for the supercomputers, both sides. It's good for HPC because HPC, we need a post-Moore's law solution. I mean, as many of you may know in this space, we are getting to a point where we cannot cram transistors on any more space. We can't make them any smaller. We're having a scaling problem. We have actually hit a parameter. We have actually hit the laws of physics in some cases of what we can do. So what's the solution for that? We're going to bring in new physics with the quantum computing capabilities. And with that, we hope to be able to continue scaling up. We're going to do that on the HPC space by looking at some of these very large codes, these very large problems, things that you would experience like in the HPC centers of excellence that Oscar had mentioned. The idea is very large codes, very important codes. Where are there potential kernels in those codes that could potentially be offloaded to QPU, to another type of heterogeneous compute? Where could we attempt to maximize, streamline, and speed up parts of the code in order to achieve results that we haven't before? On the QC side, oh, and I should also mention too, the other neat thing, kind of going back to this, we have a very rich, heterogeneous HPC compute environment, but this is all based on CMOS technology, right? So the FPGAs, GPUs, we have next-gen disaggregated systems like Cerebras systems, those sort of things, but this is all based on one sort of engineering technology. By bringing in another fresh paradigm shift, we might be able to do something pretty interesting here. Good for QC, obviously, because as qubits, as we move away from toy applications and small test systems into stabilized qubits at larger scale, we're going to have a lot more compute to be able to support it. HPC has decades of history of developing our data storage, our data manipulation, pre and post processing, all of those components that you would need, the compiling environments, the pattern and processes. We've been through all of this. The war stories we have, the lessons learned we have, we're able to apply this to be able to bring this sort of QPU compute technology into this larger ecosystem, support it, and then be able to hopefully achieve some really fantastic results. Okay, great, I hope I sold you on that. I trust I did, but what do we need to integrate quantum into HPC? So again, the short answer is a lot, and it's on many levels. At LRZ, when I first started the department 2 years ago on April 1st this year, trying to think of how we're going to approach this. And I came up with this scheme. I call it my 3x5. It's the simplest way for me just to compartmentalize the work that we are doing. And on the horizontal, it follows a typical stack. So we have to think about the infrastructure. We have to take the hardware, the software, the applications, and then the culture. This is a big one because we've got the quantum community that has been using these as experiments for quite a long time. They're doing a fantastic job, but they have a certain way of working and thinking. We have the HPC environment that's been going for decades, and their way of thinking. We've got the domain users that a lot of times don't care about the specificities of either of these polars. They just want to be able to compute. So we have to think about how we're going to all bring them to the middle and make this hybrid solution as useful and usable for them. That's the user-focused part of all of this, kind of going on the vertical. And then we also have the interesting situation that Oscar was also alluding to. It's not like these are HPC GPUs that might be new, but they're not really that new. Right? They have a long history, they have a pattern. A lot of this is very new technology, very nascent technology, and it's stuff that we have to account for. We have to account for this newness, for this complexity, for the unsureness, the kind of that chaos zone. Error correction, as we all know, is a very big thing in quantum compute systems versus where we have fault tolerance in the HPC aspect of this, more or less sorted out with research, obviously, for further optimization. So, if I boil it down to the really, really big challenges, we have the engineering of the quantum systems themselves. Then we have bringing the systems together through the software environment, through the communication, through the scheduling, all of those components. And then, of course, the big thing, obviously, then is the error correction and how all of this feeds in together to be able to give us reliable compute. Okay, nuts and bolts now. I want to talk a little bit about LRZ. Specifically, this is our Quantum Integration Center. This was taken last week. And this is a center, this is a space where we try to bring in multiple different quantum systems into LRZ. We do this as a research environment, and then we have a production environment I'll talk about in a moment. We have multiple modalities. So you'll see an ion trap system from AQT there. To the left, you will see our 5-qubit, now it's a 20-qubit, we just upgraded, superconducting system from IQM. And if you are savvy, you'll see to the far right, there is a rack with a couple of nodes in there. We have a big HPC testbed that's about 2 full racks of system that is moving down into its new home in the Quantum Integration Center in the next couple of weeks. All of this comes together, and we want to put everything in one space. We want to be able to turn the dials, to play with this for our software development, for some of our users, our select users from the community, to do some of their very specific algorithm development, mapping and co-designing with us and the hardware vendor, kind of in this triad, working together. We have them in close proximity. A lot of people say that you don't have to have them close, and that is true for certain cases, but we are looking to have them literally right next to each other, and we do that to literally have them on the same administration, the same networking, so that we are reducing any and all other parameters like latency or other factors that we would need to consider. Okay. Now, this is our compute cube at LRZ, so it's this very large building, and right now we've got one system standing in there. This is the QExa one. This was funded by the German federal level from BMBF. This is a 20-qubit system, and so this one's going to be going into service very soon in the next couple of months. We're working on the service plan and allocation strategy for that. And then we currently have a tender out for a dual system. It's going to be at least 50 qubits in the first stage and at least 100 qubits in the second stage. And this is what Oscar was alluding to or mentioning with the Euro HPC. We are one of the 6 centers that are receiving systems. Okay, now kind of getting into the hardening of this quantum technology. We have these new systems that have been in the nice warm embrace of a physics lab and under 24/7 supervision of physicists. Now we bring them into an HPC center where we don't have 24/7 physicists, where we have HPC sysadmins, where we expect it to be able to perform with a minimal amount of touch, so lower touch than what is typical, less interaction. We expect them to become more stable and operational. One of the things that we do is that we have a big telemetry project or a monitoring project where we use this for several different ways. So this slide kind of shows you we are pulling data from the QPU itself, checking the various health status on it, like the fidelities, the T times, those sort of things. We have IoT censored our quantum integration center really heavily for various things that you see on the left side. There's a couple of more because we're starting to look at cosmic rays as well. And then we also get information from the cryostat. We get information from some other sources around the building, the power, the elevators. We're also linking it to the weather databases coming from federal level, et cetera. We pull all of that together into a data center database that we have that we actually already use for our HPC centers. Systems. And what we're doing is we're starting to analyze this and starting to see if we can find potential triggers, if we can see things where the qubits are starting to get unhappy, if we can potentially track it to other environmental things happening in the environment. The idea is that when we take it from the QUIC over into the compute cube environment, we want to be able to understand if we're going to have to predict some sort of calibration event or something where we're going to have to steer the users off in order to be able to do dynamic resource allocation so that as a production type of system, we can honor the SLAs that we are bound to. Additionally, so not only is it for the operations part, but we also feed several of that data to the users through a portal, or sometimes called cloud access. We feed that for the users, for them also to have the information, things like the temperature of the qubits, other parameters that they would find necessary for their work. So this is one big project that we have going on, again, as part of hardening quantum systems within an HPC environment. Okay, now, all of this is software. At the end of the day, this is all software. So the one big thing that, aside from having the systems that we are known for and that we're investing quite a bit of effort into, is our software stack. So it is called the Munich Quantum Software Stack. It is really responsible, and we, again, because we come from MQV, where we started right from the beginning with 3 different modalities and figuring out how to unite it with HPC, we are looking for a very flexible, extendable, comprehensive stack, full stack, open source that allows us to be able to integrate this into a supercomputing environment, accounting for the different modalities, their uniqueness, but then also their commonalities. This is feeding, so you kind of, my diagram here, the MQSS is contributing to or drawing from parts of various projects at the Bavarian, national, European, and global level. So it's this kind of a conglomeration. Bits and pieces are built from different projects. We're bringing this all together, and then we're hoping to raise this and build a really nice fat middleware layer for our user base. So really quickly, this is approximately how it works. This, again, we're kind of taking something 3-dimensional and squashing it, and then we're also kind of capturing it at a snap, at a point in time. So this is not completely how this would work over the life cycle of the shot, but it'll give you an idea. So basically, we have, on the left side, we have the programming abstractions, we have the toolkits, frameworks, things like Qiskit that you might be familiar with, the users might be familiar with. We're not abandoning that. They can still use it. We have other things that are maybe domain specific, so it's kind of at the lowest level, something like Qiskit. At the higher level, it would be something like domain specific interfaces, like in CFD, molecular dynamics, et cetera. The top part up there is, it's a web portal access. Again, sometimes this is called cloud access, but basically it is a way to directly hit the quantum system without going through the HPC. And we do this because this is the comfort level of users presently, and there may be a slice that will stay that way, but this pathway goes through, it hits a scheduler, goes through the compiler environment to a backend, which is a sync point between the compiler, the representation language, and the quantum system itself. That's the QDMI. More interesting, as an HPC center, we also have a path coming through HPC. So as a typical HPC user, you would log in, you would go into your login account, you would do your code, you would compile. The kernels for the quantum components would then go through their own path, through their own quantum compiler. This one is a little bit interesting because we're using quantum intermediate representation. So QASM, you may know about, developed by IBM. For the superconducting path, QIR is an open source community effort that is meant to be agnostic to technology and to account for the different modalities. We are on the steering board for this, which is fantastic because we are implementing it in a real world space, and we're able to help contribute to this effort just based on our own sweat and tears that we're doing as we develop this. So the pathway then, as you get back to the quantum systems, you also see something there called figures of merit. So the idea is such. The blue that you see right now, this is a common standard baseline for all systems. This is the commonality among them. But we cannot be so naive as to think that we'll just be able to offer a common solution, completely agnostic, everything will work fine depending on the different modalities. There's physics involved here, these systems are different, there are unique characteristics of them, and we have to account for that. So we do that by understanding first the figures of merit of each system, and that informs the compiler for part of a dynamic flow. These are things as simple as the fidelity, the t times, other parameters that the compiler would need to know to be able to dynamically work with the compute and to be able to run, thousands of shots, do the statistical average, send that back to the HPC part of the code, etc. So we do have to have awareness of the quantum systems. What we've done is we have the baseline, and then we have what we call separation of concerns. And what this means, what you see, these little boxes, these are the points that we have identified that kind of are a layer of abstraction lower that are specific to the systems themselves, okay? So, for example, when you get to the system selection part, so when you're getting to the scheduler, before you go and hit the compiler, you need to know what sort of system you're going for. And there are different parameters. You also have to analyze the code. Some domain users are not going to care which quantum system it runs on. Actually, probably at the end, most are not going to care. They're just going to want faster compute. So we want to be able to analyze the code, see which parameters best of the code of the algorithm best fit the system. We want to be able to select it, and so we have to know specificity of the systems in order to do that. Compiler passes are basically, you are streamlining the QIR. So the QIR has a whole lot in it, but the compiler passes are going to look at the code, go, okay, you don't need this gate, you don't need this, you don't need this, you don't need this. The system that you are selecting to use does not need this or needs this, and so it creates a unique pass of specificity in order to optimize and speed up and be more efficient as it sends it over to the quantum system. I mentioned the FOMAC library. That's basically the operational parameters of each of the quantum systems that come into play. That's get built. And then there's an interface between the quantum backend interface and the system itself in order for it to communicate with the pulse electronics and any other specificity at the hardware level and the firmware level for the vendors. I'm going a little bit fast because, of course, I am running out of time, as I tend to do. You'll see that I could talk about this all day, as you can probably imagine, and I really do need a timer and a cowbell to shut me up. But what you'll see here is that not only do you have the individual parts, but again, for the neutral atoms, the superconducting, the ion, they each has their own flavor. So ideally, what we're looking at is having basically an API packet for each system that has a couple of different touch points that we work with the vendors, put all that together, plug it in to the system, kind of Lego-like a little bit, and then we should hopefully be able to operate. Now I say should, we are further than that. We've already done it with a superconducting system. We have the ion trap system that's coming up now, so that's the next one, and we have a neutral atom system that we're working on with Max Planck. Okay, actually I'm good on time. Our problem, race, and then, I have 32 seconds. What we're describing is not unique. We are one center in Germany, we're one center in Europe, we're one center in the world. This technology is going to start flooding into HPC centers everywhere. And we realize that, and so working with partners that we work very closely with at Oak Ridge, at iCheck in Ireland, Los Alamos, TUM, the Technical University, and LRZ, we went to the IEEE Quantum Initiative and we said, hey, we think it's time for a quantum HPC working group. You'll see the spoke that we came up with. It's basically a representation of that 5-layer. So it's all these components, skill development, infrastructure, the hardware, the software, all of those components. These are problems that we all have, and so there's strength in numbers. We would absolutely love, if you're interested in this, you can hit that email there, or that URL there. You can also talk to me. We have several events that we're starting to plan. We kicked this off last year, and it's now going very nicely. If you would like to join us, we would absolutely love to have you. More brains are always better. And with that, just a last round of what we're looking at with our 3x5 model, how we're approaching it. Definitely would love to hear your perspective, your approach, and see if we can't crack this together. So thank you very much for your attention, and I hope that was interesting for you.